Hi everyone and welcome back. We're going to go ahead and go into our next topic of heat and heat transfer methods. So let's go ahead and start with the idea of heat. I want to remind you that hopefully you guys even think of this in real life. When two objects come into contact with each other, energy will be transferred between them from the hotter object to the colder object until they reach equilibrium. Okay, think about when you put ice in a cup of water. Okay, that ice and water will continue to transfer heat between the two until the ice is fully melted and it has reached some kind of equilibrium at some temperature. Okay, hopefully a colder temperature, right, than what the water started with. Okay, and that's what we are going to be looking at a lot today. Okay, I also want to remind you that no work is done because there are no forces that are acting through a distance. Remember that work equals force times some distance. And the transfer of energy is caused by a temperature difference. Okay, if there's no temperature difference, there won't be any kind of transfer of energy. Okay, now heat is the spontaneous transfer of energy due to a temperature difference in the form of energy. Okay, and we'll look at this a lot today. I want to let you guys know what the unit of heat is. In SI units, it's going to be joules. Okay, since it's a type of energy. We also go by kilocalories or kcal, and that's going to be the energy needed to change the temperature of 1 kilogram of water by 1 degree Celsius. Okay, that's how it is defined, 1 kilocalorie. Okay, so with that, let's go ahead and talk about the mechanical equivalent of heat. Okay. This is going to be the work needed to produce the same effects as a heat transfer, okay? And it's defined as 1 kilocalorie equals 4,186 joules. Okay, so this was defined as with water, okay? And James Prescott Joule performed these experiments to establish this relationship. Okay, so what he did was tried to figure out, using an apparatus, okay, figuring out what is the mechanical equivalent of heat, okay? And we will be looking more in depth at this in your lab this week, so I wouldn't worry too much about everything here, but you will be figuring out mechanical energy turning into different types of energies, okay, and how heat might be involved in that. Okay, so you'll be looking at that in your lab this week. All right, let's talk about temperature change. So temperature change has to do with heat transfer. Remember, if you're heating something, you have an increase in temperature. If you're cooling something, you have a decrease in temperature. Okay? Heat depends on 3 different factors. So that change in temperature is important, the mass of the system, and the substance and the phase of the substance. So what is it, the type of substance, and what phase is it in? Remember, we have 3 different phases. We have liquid, gas, and solids. Okay, so keep that in mind. These are our phases. And we come up with this relationship here. Okay, Q, or the heat transfer, is equal to M, our mass, times C, which is a specific heat, times our change in temperature. Okay, now let me mention specific heat real quick. That depends on our material and what phase of matter we have in our substance. Okay, so a solid versus a liquid, or a gas versus a liquid. Okay, so that C, or that specific heat will change depending on those. Okay, so we have a figure here, and that's just to show you this relationship that our heat transfer will be different. Okay, so in this first one, we have our heat here, our mass, and our delta T. Now, if we take the delta T and we times it by 2, that means our heat will be times by 2. Same thing with our mass in part B here. If we multiply our mass by 2, or increase the mass by 2, then our heat will be increased by 2. By a factor of 2, I should say. Okay. Now in this case down here, if we have different materials, so this is copper and this is water, okay, our Q will be different. The only thing that's left is that C, our specific heat here. So in these cases, our specific heat of copper is not the same as the specific heat of water, okay? And a lot of times you'll see me write subscripts like this, okay, when I'm doing my specific heat, because it can get a little bit complicated when we have different materials, okay? All right, so a little more on specific heat. Again, it's the amount necessary to change the temperature of 1 kilogram of mass by 1 degree Celsius. In SI units, we can express it as joules per kilogram Kelvin, or joules per kilogram degree Celsius. Other units, we can put it in terms of kilocalories per kilograms degree Celsius, okay? And I wanted to note another term here, and it is called heat capacity, okay? And heat capacity is related to specific heat in such a way, okay, heat capacity is now capital C, and it is going to be the specific heat times the mass of the substance, okay, or the change in heat over the change in temperature. Okay, this is called heat capacity. And I point this out because this will be important in your lab this week, okay? As the amount of energy required, so that's delta Q, okay? So as the amount of energy required, Q, to change the temperature, okay, as that energy required increases, the heat capacity, and therefore the specific heat, increases. So as this required goes up to change delta T, that means that C and little c will also increase, okay? This may be a little bit confusing right now, but once you go in through your lab, you might be like, oh, I remember her saying something about that. So you can come back to this and read this over again, okay? All right, so let's go ahead and go into our first example, 14.1, and it is a little bit long, but it's got a lot of aspects in it. So we're gonna go ahead and walk through this, at least started in this video. Okay, so we have a aluminum pan on a stove, and that has a mass of 0.5 kilograms, and it's used to heat 0.25 liters of water. So this is the mass of the aluminum pan. I'm going to put AL. My mass of, actually this is a volume, right? So, because it's in liters. So my volume of water is 0.25 liters. And we're using it to heat the water from 20 degrees Celsius to 80 degrees Celsius. Okay, so this is, I would say, initial, TI, and T final. Okay? Now, it states how much heat is required. That's going to be our first part. How much heat is required? Okay, so our first step, I guess, would be, what equation are we going to use? Okay, well, we did just state that heat is equal to mc delta T. Okay, so we know we're going to be using that at some point. Okay, we know that we are trying to increase our water temperature, right, with an aluminum pan. So now what we will do is we'll want to figure out the entire amount of heat, or the total heat, Q total, I'll say, for this to happen. Okay, so my total heat is going to be Q of the aluminum pan plus Q of the water. Okay, so my first step is going to be determining my delta T. Okay, so my delta T is going to be my final temperature minus my initial temperature. So that's going to be 80 degrees Celsius minus 20 degrees Celsius. So my delta T is then 60 degrees Celsius. Okay, so that's my first step. My second step is going to be determining my mass of the water. So remember, in this problem, we were given the mass of the aluminum, but the volume of the water. So we need to figure out how to relate this back to mass. Okay. Remember that density equals mass divided by volume. Okay, so this is how we are going to relate it back. So let's take this equation and rearrange it to equal mass. So mass now equals density times volume. Okay, and if we want to find the mass of the water, we'll take our density of water, which is 1,000 kilograms per meters cubed. Okay. And then we have our volume, which is 0.25 liters. Okay, but now we have liters and meters cubed, so we need to multiply in order to cross those out. So let's see. In 1 meter cube of water, there is 1,000 liters. Okay, so now all of my little factors here will cross out, except for kilograms, which is good because we're looking for mass. So now my mass of water is 0.25 kilograms. Okay, so this just works out nicely because of the density of water. If you're looking at a different substance, it may not be exactly like this. Okay, so just pointing that out. Oh, I don't know why I'm circling this, but there we go. Okay, so we have our mass of water. Now, our first thing that we want to do is find out our heat transferred to the water. Okay, so again, Q is our heat transferred to the water. Okay, so that is going to be equal to M sub W C sub W times delta T. Okay, so our mass again is 0.25 kilograms. Our C is going to be in a table, or how we have, oh, there we go, how we have defined kilocalories. This is actually the same number, oddly enough. So it's going to be 4,186 joules per kilogram degrees Celsius times our delta T, which is 60 degrees Celsius. And so our heat transfer to the water is 6.28 times 10 to the 4th joules.